the month here, we have spent about several of us students and others also benefiting from that. Good folks who wanted to use courses. Then we had students who were again welcoming from the campus for summer school in Yahoo, to academia, to industry, then again to CMU. That time I asked him to do it. So now he's in Amazon Web Services, and now he is kindly with us. So, I mean, as usual, we look forward to trying to talk. And I think Alex is here, probably to tell us more about what cutting edge machine learning is happening, not only at Amazon, but I guess at the cutting edge of machine learning itself. Right? So with that, we look forward to Alex.
Okay. So thanks a lot for the kind words, and yeah, I'm happy to be back here. It's been 7 years since I was here last time. Somehow a lot has changed, and somehow not so much has changed, and I guess it's a good thing. So today my talks, so you're getting a double feature, right? So apologies for making you all wait a little bit. The first talk's mostly about computer vision. Second one is mostly about deep learning on graphs. Actually, they are both on deep learning. And the talks that I'll be presenting today are very much engineering, software engineering library focused, as in, how to actually get started on this. The reason why I made you wait a little bit right now is I was trying to set up something specific about the demo, and it didn't quite work in the way that I wanted it to. Basically, I wanted to use my phone as an external camera, and it's sometimes a bit flaky. And yeah, okay, so you'll see the demos nonetheless. Okay, so who does computer vision here? Yes. Oh, okay. Then let me start with the graphs first. Okay, nothing easier than that. Okay, sorry about that. Okay, that's an easy fix. Okay, so deep learning on graphs then it is. Okay, so. Yeah, sure. Don't worry, it's fine. Yeah. So, who's worked on graphs? Okay, nice. Who does deep learning? Okay. Okay, that's good. Now, who does graphs and deep learning? Okay, so there's not a lot of hands up, right? So you might wonder, why on earth is that? And if I'd asked about that in computer vision, I mean, there would be a lot more hands up. Like you can pretty much not do deep learning, computer vision without deep learning anymore, as in it's a very nice non-parametric estimator. And part of the reason why that's the case, that there aren't that many hands up, I think, is because there isn't quite the same amount of software library support, software tooling, which separates the software engineering part from the modeling part, right? Because, if you want to do computer vision, you take, your TensorFlow, PyTorch, MXNet, or Caffe model, or whatever, and you write it up, and then you say, deep learning framework, please now run this thing efficiently, and I don't want to have to bother with this, right? You'll have to bother a little bit, but not too much. Anyway, so what we are trying to do is do the same thing here for graphs. And I'm the guy who gets to travel and talk about it, but these are the guys who actually did all the hard work. So this is my Shanghai team led by Zheng Zhang. Then in Palo Alto, there's Da Zheng. There's Minjie Wang, who's at NYU and who's actually just about to join the Shanghai lab. By the way, that team is hiring. So if you're looking for a job and you want to spend some time in Shanghai, okay, reach out to ZZ and he'd be delighted. Yeah, and so I'm Alex. Okay, so let's see, does this work? It was working before. Hey. Okay. It'll work. No, it does. Okay, so we'll talk about graphs first of all. So a little bit, what you can do with them. Then we'll do a quick connection to graph Laplace and other things, and then it'll go and we'll dive deep into deep learning and frameworks and models and stuff. But let's start. Okay, I think it's the battery. If somebody has a spare battery, that would be great. So can I give you this and you'll... Yeah. So let's start with a graph of lots of nice people, right? So there's like Vladislav Shurkov and Putin and Medvedev and so on. And, they're all Russian politicians, and they do what Russian politicians do. They kind of probably bribe each other and threaten each other and kill each other. And so it's an interesting graph, right? And so what you might want to do is you might want to perform... that kind of takes away the things if the slides move by themselves. So, you might want to do interesting things, like you might want to regress on a vertex or on an edge, like, what's the relationship between Boris Yeltsin and Anatoly Chubais? Well, who knows, right? But maybe I know that Putin, really didn't like this guy and wanted to have him killed, and maybe I'm making stuff up, so I hope that there's no member of the KGB here. But the point is, you want to get some meaningful feature embeddings, right, for the vertices and possibly for the edges, and then to do something with it. Okay. If we are not interested in Russian politicians, at least we might have a graph, and we might want to do fraud detection or social recommendation, or you might want to fuse data where maybe I have some graph information and then I have some additional data, like I have photos, right? Or maybe, some textual descriptions or their posts, and, or maybe they interact with each other by sending each other emails. So in general, I have some graph, G, with some vertices and edges, right? This is like the general description, and they might all come with attributes. And so one of the goals that I might have is, given some vertex labels Y, estimate the remaining ones. So for instance, I know Chiru is a nice guy, and Chiru hangs out with his PhD students, so I'm assuming Chiru only hires nice PhD students. And then, of course, their friends also might be nice, but at some point, maybe somebody of their friends of their friends of their friends is maybe not such a nice person. And so exactly, how do we propagate this through, right? Or maybe I have some edge attributes, and I want to, figure out the remaining ones, like, hey, maybe Chiru should write the paper with, I don't know, maybe we could write another paper, right? So that's the point is, you basically want to do link recommendation. So, how would you do this? And in the good old days, what you would have done is, for instance, for regression, right? So you have some vertex labels. You want to find some function f, and I'm taking some liberty in saying it's a function because actually it's a glorified vector, right? Because we have a finite countable set of vertices, so it's really just f1 up to f1000 if I have 1000 vertices, and I want to minimize the loss between the values fi and yi. And so then I would like to infer for additional unforeseen values, how, new vertices, what the values are. Right? And the problem is I need to have some idea about, the smoothness of that graph, right? So maybe, adjacent neighbors are similar and something like that. Okay. So what I could do is I could, for instance, use a feature-based approach. So a feature-based approach would do the following thing. I have some function fi, which is, W transposed vi plus maybe some bias, maybe some nonlinearity. And then I can go and, start hand engineering lots of features. For instance, the degree of a vertex is a useful feature. The degree of its neighbors is a useful feature. The degree of its neighbors is a useful feature, and so on and so on. Or I could start with random walks emanating from a vertex, and then, I get, something like vert to vec, but in this case, walk to vec, and people have actually done this, right? Or I could just take the k-step neighborhood and I fingerprint this. And I'll talk a little bit more about this in detail later on, so the ViceFellaDamon algorithm will give me that. I could also just, open a random page in linear algebra and look at what people do with matrices, and I can do this interesting thing also with a graph matrix, and then say, that's my new feature, and guess what? This is worth a couple of $1 billion. Right? It's PageRank. They actually thought deeply about it, and we'll get to that in a moment. So this is one approach how I can do learning on graph. By basically hand engineering features, and I would argue for about half a century, people have been doing this. There's an alternative, which is I define smoothness over the edges, right? So for instance, because Chiro and I are friends and Chiro is a nice guy, you might think that maybe I'm also a nice guy. And that might be true, it might be not true, right? But basically, if you set this up accordingly, so you have I related to J, right? I might then say, well, maybe the embedding between Fi and Fj should be similar, so Fi minus Fj squared. And so if you use, high-tech, math tools like the second binomial formula, you can expand this into di Fi squared minus, some overall edges I and j, between I and j, Fi Fj. And that gives me F transpose D minus G F. Where D is the diagonal matrix of degrees, this is the graph connectivity matrix, and that's the function value. So this gets us to state of the art about 1971, 1972. I think the Fiedler paper was from 1972, which is the second largest eigenvector, because the first one is just the stationary distribution, so nobody cares. It's stationary uniform. But you can do that. And then we looked at that problem in 2015, 16, Yushang Wang, Ryan Tibshirani, and others. I also, attended some of those meetings. So yeah, but basically, Yushang really did the algorithms in there. Well, you could also use something like an L1 penalty. Yes? Yeah, so basically Fi and Fj could be scalars. They could be entire vectors for, proper feature embeddings. And I would say if I and j have an edge between them, so in an undirected graph, in a directed graph I have to be a little bit more careful, but you can, define directed graph Laplacians and all of that. But basically this way, you can say, well, if I and j are connected, then maybe their embeddings or their values are somewhat similar. And so the L2 version is basically what Fang Chung and Fiedler and others did, and that's basically about 40, 50 years old. And then in the 2010s or so, well, maybe late 2000s, sparse coding became popular, and so people started exploring what you can do with L1. So at some point we figured, okay, let's ask questions like, what would an L1 theory of graph smoothness look like? This is essentially then the extension of what we did with trend filtering. And so there's this paper called graph trend filtering, and that's what I'm referring to. This actually works fairly well, except that it's very costly. So it works better than the Laplace Smoothian. So this is Laplace, and you can actually define an entire series of kernels from that. But if you use graph trend filtering, it works quite nicely. This is actually Allegheny County, so this is where Pittsburgh sits. And yeah, we did some regression there on some data, and it worked nicely. And you can prove lots of nice theorems. And if you want to read a lot of math, this is a good paper. Okay, so, and if I'd given that talk maybe 3-4 years ago, I would have probably given that talk, and we would now have continued with about 40 minutes of math. Alas. So I guess everybody knows this character, right? If you play Fortnite, this is Mr. Vertex. So let's go back to that ViceFellaDamon algorithm. And it'll become clear in a moment why this matters. So the ViceFellaDamon algorithm is an algorithm that allows me to solve, or at least in some cases solve, the graph isomorphism problem. So graph isomorphism problem is I give you two graphs, and you have to tell me, are those graphs the same? And that sounds simple, but if your graph is really large, then getting all the permutations right is awful. However, there's a nice way when I can actually solve this problem easily. And that's the case if all the vertices have a unique label, right? And it's trivial. I mean, then you can give that to, a first semester student and tell him, hey, compare the graphs, because all you do is you just go over, the IDs of the vertices, and you compare for every vertex whether the connectivity structure is the same, and I'm done. Okay. Now, how do we turn a unlabeled graph, or only partially labeled graph, into one with unique IDs? Well, what I can do is I can simply, let's say we start with no labels whatsoever, I assign every vertex the label 1. Then I compute the hash of the vertex ID and all of its neighbors. Okay, so now I've already made all the vertices unique according to their degree, right? Because, depending on how many neighbors they have, I'll get a different hash, and I'm assuming that I don't have collisions in my hash function, right? Now, once I have this, I can, so this is Base's update function, like hash of vertex ID and of all of its neighbors. Some local update. What I then do next is I perform the same operation again. And now it's going to take into account not just my neighbors, but also their neighbors. And I keep on doing this. And so it's very easy to see that at every step, the number of non-unique vertices can only decrease. Because once it's unique, then the hash of that, since I've just defined a way the collisions, will never collide again. So that's fine. And the algorithm will terminate at the point when, well, basically, I no longer split any non-unique vertices, or when everything has become unique. Okay. So the result of that is that you can easily, run this algorithm, and if you get lucky, you're done. And if you're unlucky, then, well, at least maybe things are easier. Thanks for the whiteboard, because I will now show you an example where this doesn't work.
The talk is streamed in full time.
Okay. Okay, so here's an example of a graph where this fails miserably. Because it's very nicely symmetric, right? So in this case, well, I'll basically assign all of those vertices the label 1, a hash, and then I get the new hash, but that's the same throughout, so I get nothing. Okay. Let's make life a little bit easier. Let's attach this guy here. So now life has become actually quite easy, and you can see that I'll basically be able to identify this one here, this one. Now these will all have the same ID, and these two will have the same ID. Now, if I wanted to make life a little bit better, I would have to break the symmetry. For instance, I could add a triangle here. If that happens, then I'm done. On the other hand, if I were to attach it here, it wouldn't do me any good. So nonetheless, if you look at those features, they're pretty useful. And as a matter of fact, you can design a very nice graph kernel based on that. And that's precisely what Karsten Borgward and Nino Shavashidze did in 2013. And the important thing is, so they have this local vertex update algorithm, which then leads to very good features. And they got a best paper prize for that. This was, and still is, probably the fastest, kernel on graphs type algorithm by actually generating features. And so when I saw that paper, I was super happy for them, and I congratulated Karsten, and I said, well, that's great, but can we do features? Okay. And, yep. Well, the complexity is number of vertices plus number of edges for a single update, because you need to incorporate, all of its neighbors, times L, where L is the number of iterations. So the problem is it's not guaranteed to give you a polynomial time graph isomorphism algorithm. Nonetheless, in practice, it actually works quite nicely. Right. So it's not guaranteed to give you an answer, but when it does, it's polynomial, right? So so that's the thing. So if you're unlucky, well, you're unlucky. Nonetheless, for machine learning, this is perfectly good enough because you can just say, well, I make at most 10 iterations and that's it. And so I said, well, that's great, and it worked well, but can we add features? And yeah, we tried that. I talked Carsten and Nino into it. And Nino did a lot of work for half a year, and she tried and she tried and she tried a lot. We tried a lot of different things, and we failed miserably. That project was a total disaster. Okay. So why am I mentioning this? Well, because I'll show you afterwards how you can actually make it work. So then, another algorithm that can also be written as a vertex update. PageRank. So everybody knows PageRank, right? So for recap, this is the random surfer with probability epsilon. You just pick a random vertex, and with 1 minus epsilon probability, you follow one of the links from vertex I to j. And then through the balance equations, you get those weights. So you have to divide by the degree of the vertices, and you get that. Okay. So you can then take this and you iterate until you're converged. So one way is you simply run this update until you're bored or run out of compute or whatever. Or you can be clever about updating mostly for the vertices that are not stationary yet. And you can write this as a self-consistency equation. But here's the crazy thought, like if we didn't know this equation, right? So, to some extent, Page, Brin, and Motwani, I mean, this was a very ingenious idea. And mind you, John Kleinberg had essentially the same idea with hubs and spokes, but he didn't get quite as rich. But well, if we didn't know this function, right, could we learn it? And hold that thought. I'll first show you a little bit on how you would actually go and solve this with DGL. And so every talk on graphs needs to have Zachary's Karate Club in it, I'm afraid. So this is basically that Karate Club, which at some point, split into two groups, right? And you can see that there aren't that many edges between those two factions. But what you can do is you can just define that in DGL, and you do that by, giving it a vertex list and an edge list, and yeah, okay, gives you a graph. So the reason I'm showing you this is because, DGL isn't that scary beast. You can just, use it to define a graph in a fairly pedestrian way if you want. Then you run PageRank. So PageRank, you basically use the following thing. You essentially need to PageRank value. You need that. So you basically take this value and divide it by the degree, right? It's another n data part, right? So node data, PageRank value, and so that we have a dictionary here. And then what I'm doing is I'm sending a message. So update all. So you send a message, copy from the source, go from PageRank value to this message. And then I need a reducer, and that's basically just summing everything. And then there we go. This is basically just the PageRank update. 1 minus damping factor, that's my epsilon, or n plus damping factor. This is just, it goes everywhere. So this is not the world's most efficient way of doing PageRank, but it's fairly straightforward. And the good thing is DGL takes care of all the grunt work behind the scenes. And we then work hard to make it efficient. So who's doing graphical models? Okay. If nobody does graphical models, then I can pretty much skip this, but message passing there looks very similar. So again, this looks like vertex updates, and can we learn them? And well, I guess I've now asked that question 3 times, so the answer has to be yes, because otherwise, what would be the point of this talk? So this is what gets us to graph convolutions. And it's an idea from Kip van Welling, 2016. And basically, the idea is you have vertices and vertex and edge features, xi and xij. And then you compute new vertex and edge features using some local update function, which depends just on the vertex features and the edge features. And then you have basically two options. You run this a fixed number of times, or you run it until it's converged. That leads to slightly different inference algorithms, but that's about it. So then, okay, this is good, and that actually works quite nicely, and this is what's then called graph convolutional networks. I'm not sure this is the world's best name, but that's what stuck, because that's what Kip and Welling called it at the time. What you can do is you can also use the fact that LSTMs or GRUs or RNNs overall make everything better and have an additional hidden state. So you can have the same update functions with that. So you basically have an LSTM which takes into account the local vertex and vertex state and all the neighbors. And as a matter of fact, that's in GeniePath. Now, the fun thing is this is also in a paper that Platanios uploaded in 2018. Now, here's the interesting tidbit. That paper is pretty much verbatim a paper that was rejected from NIPS in 2015. Yeah, it's just that, that guy couldn't be bothered doing it and did something else for his PhD, so he missed out on a lot of papers. But that's what happens if you go to industry, then you don't have time to necessarily follow a lot of speculative things if something else is higher priority. And I think we had good fun otherwise, but you win some, you lose some. So, minor twist, the LSTM update function, right? So this takes, of course, in general, you have this function that takes the input from all of its adjacent vertices. Now, this is a function defined on sets. Why does that matter? Because since it's defined on sets, since the order doesn't matter, it drastically restricts the class of functions that I could be using. And there's a little theorem. This is basically the deep sets theorem that Mansil Zahir proved. Basically the hard work was to go and do a Google search on a group theory result from the 30s. I thought, well, that result has to exist, and then we just looked for it. Namely, that any function that is permutation invariant can be written as the aggregation, as the nonlinear function of an aggregation of nonlinear function of its arguments. So basically no point in being super fancy here, and this is pretty much all that's needed. Okay. And then you run this. Now, of course, LSTMs make everything better. Attention also makes everything better, right? So, of course, what you can do is you can use attention weights in addition to this aggregation. And there are two papers, one which just does this for deep sets, and one does it on graphs. Actually, this predates the deep sets with attention paper. So much for that. But basically, you just use a weighting function which depends on the vertex state, and then you get something that's slightly more accurate. That's called graph attention networks, or GATs. Now, graphs are much more pervasive than that. You can use it for NLP. So rather than one giant graph, you might have a lot of small ones. Right? You have a parse tree, and then you can, in a tree LSTM, you might write it as a graph, or if you have transformers, you can write them as a graph. And in this case, it's just dependency graph over the values. And once you have it written as this, you can ask the question, well, can I do something here to make this graph a little bit nicer to deal with? Turns out, yes, you can. And so if this is your standard data flow in a transformer, you can sparsify that, and that's the star transformer, and it's a lot less data hungry. And you can then use the seg tree transformer, and that's that's somewhere in between, and it works a little bit better. So basically, there's plenty of work that you can do there. And now it basically means that you can experiment with a lot of graph-structured deep learning architectures and just let DGL take care of all the hard work. Of course, there's the entire issue of, how do you make it work? So here's the challenge. And that's something that took a long time until people got it right. So you've probably heard of the 6 degrees of separation, right? So if I take the Facebook graph, let's say I have, a billion vertices approximately, maybe a bit more by now. Well, then, it would take, only 6 steps from one vertex to typically reach pretty much every other vertex in the graph. Okay, that's great for information diffusion, but it's bad for gradients because any vertex update affects the next update, the next one, and the next one. So after 6 hops, I need to run backprop over the entire graph of a billion vertices just to update, to get the gradient for one puny vertex. And that means the algorithm is computationally entirely infeasible. You can use that for batch gradient descent, but not for stochastic gradient descent. And so what are we supposed to do, right? One way how to do it is you say, well, I'm going to subsample only a small graph out of this. And so just like what you would do in BPTT, backpropagation, so truncated backpropagation in the sequence model, you just terminate early and you don't worry about the rest. So you basically detach the compute graph. And then you compute the gradient only over that subgraph. Okay. So therefore, what we've done is we've traded something that we can compute exactly with something that we can only estimate. So I've drastically increased the variance, but it's still more or less unbiased, and there are various variance reduction schemes that, of course, you should be using. And, well, that helps me on the gradient computation side. There's still one big problem to solve, right? So now I've updated my weight vectors. And now, of course, my entire embeddings are stale because I have no new weight vectors. And so therefore, my gradients, so my parameters on my embeddings with that would also have to change. So if I go and have to change, the embeddings for, a billion vertices, I'm no better off than before. I've gotten a speed up of a factor of 2 at the expense of some variance, but it's still stupid. So what you do instead is you actually only update some of the vertices. So with that, you get somewhat stale vertex values, but in exchange, you get a significant reduction in computation. So that's the trick. And in doing that, you get something that's actually computationally tractable, and it works quite well. Okay. So now I've bored you for long enough with theory. You probably want to see how this thing actually works, right? So enter deep graph. Yes? Yeah. So the subgraph sampling, you can control separately, and you can control the sampling policy. That will give you different algorithms and different implementations. And the thing is, for some of them, you may be able to prove some things. So for instance, you can prove that in certain cases, you will reach stationarity, basically by just arguing, well, the more I'm converging, the less my vertex embeddings will change. And so therefore, the effect of staleness will be reduced. And so essentially, as you're converging, everything gets better. And then if everything is nice and Lipschitz and the constants work out all right, then things are okay at some point. And that's kind of a simple sanity check, but it doesn't amount to much in terms of a convergence proof otherwise. But that's probably the best thing you can currently get. In terms of computational complexity, well, that's really up to you how you engineer your updates. Right. Now, let's actually see how you would do this in practice, because that's the even bigger headache. So deep graph learning, so DGL.ai. So I'm quite confident right now we're the fastest guys on the block, but it's still early days. And yeah, so there's a GitHub repo, and not just that, there are lots of tutorials that go with it. So this way, if you actually want to figure out how to program in this library, go and have a look at it. The API is still improving because we're still learning what works and doesn't work, and the algorithms haven't entirely converged yet in terms of what's commonly accepted as working. But it's a big step forward if you want to try out new ideas. Let me just give you another data point why the world needs something like this. So if you look at the iClear author's reply for the graph attention network paper, you don't need to read the details, but basically they said something like, well, yeah, we would have wanted to run on a larger data set, but we didn't know how to do it. So we were basically, or at least we were basically at that same point where people were in deep learning before deep learning frameworks became a thing. And so you need to separate the engineering from the machine learning, because engineers aren't necessarily good machine learners and vice versa. And here's our feature set, and of course we have checkboxes everywhere, whereas everybody else doesn't have checkboxes everywhere, because otherwise I wouldn't be showing you this, right? But I'm fairly confident that what we have is actually a little bit nicer. So what does it actually mean? You can send arbitrary messages, edge-based ones, vertex-based ones, or some combination of that. You have a choice of different sampling strategies. So if you come up with a new one, you can easily add it. We can deal with different types of graphs. So that means you can use it to, for instance, experiment with new NLP designs. But you can also use it for a giant graph. And if you like MXNet or PyTorch, well, okay, the choice is yours. You can implement in both. The reason why we can do that is because we basically have DGL taking care of the graph aspect, and we have the underlying deep learning framework taking care of the backdrop and all of that. Why would we do that? Well, because we didn't want to invent yet another new deep learning framework, with the result that then, with that yet another deep learning framework, now you need to re-implement your ImageNet, right? So what kind of messaging can you do? Well, you can send and receive between, vertex I and vertex J. You can combine send and receive. You can propagate, or then, you have some arbitrary UDF that takes care of things. So let me show you a little bit what happens in messaging. So we have this lonely vertex U, and it wants to talk to some vertex V. And so what U wants to tell V is, hey, I have some data, right? So I have some source data, some edge data, and it needs to go there. That remote control works sometimes. Okay, so we send a message, and that goes into this mailbox, right? So because there might be various vertices U that want to talk to V. And then the vertex V at some point goes and reduces, just in a standard MapReduce type of operation, by aggregating everything, right? Now, here's the nice thing. That's what you code. This is what we do, right? So it's all nicely patched up such that you get good performance on the machine. So the user defines a computation on a batch of nodes and edges, and you just, have a message function, a reduce function, and then everything else works. So let me show you what that means in practice, because that sounds a little bit abstract in theory, and is probably a little bit fast. So remember, we have graph convolutions. So you take the input graph, and then you take an update where you take the vertex and its neighbors, and you aggregate and apply a ReLU, and you do that again, and then at some point you get an output. So let's code this up in DGL. So here's the code, and geez, it's really not very well readable. But basically, what you first do is you define a message, and so GCN message, which basically takes a tensor for a batch of features and source nodes, and okay, that's what you want to send. And then, we have a forward function. This is, the standard forward function that you would have in your favorite deep network tool. And so then I apply. So by the way, I have to define a linear function and an activation, just like in any other MLP. So this looks exactly like what you would have in an MLP, just that we use it slightly differently. Because what you do is you now sum over all the messages. You apply the linear function, and then you apply the nonlinearity. And so now that I've defined this, I can define the entire network. I would go and take the graph. I have this twice. Basically, I have this GCN message and then the reducer, and I combine this. And yeah, that doesn't really do DGL a lot of justice because it's really quick, and doing software in public that you've not seen before and trying to parse the code is hard. So I strongly recommend that you look over the source code afterwards. There's plenty of that in there. So these are all the networks that we have. That list is probably out of date because it's like a week old. People are starting to contribute quite a bit, so it's good. Now, why does it work? Well, we have DGL sitting on top as the thing that handles the graph part. Then we have deep learning frameworks, and so PyTorch and MXNet are covered. If somebody wants to write an eager or a Keras imperative version for DGL or a chainer version, that would work. Keep in mind, this only works for imperative code. It will not work for symbolic. Okay. Now, what you want to do then is you want to push that into a deep learning compiler, such as TVM, and then you execute it on GPUs. So this aspect is still work in progress. Expect a lot of progress around TVM before the end of the year. So Tensor Virtual Machine. It's basically if you don't want to write CUDA code but would like to have more high-level code for defining operators, TVM is probably what you should check out. Yeah, and this isn't just all talk. This actually works. So what we did is we compared to all the existing implementations for the same networks. And while we are typically quite a bit faster, if you then compare to PyG, so Python geometric, we're faster as well, and we use less memory. Like on Reddit, they run out of memory and we don't. So this is through automatic batching. This is through kernel fusion. So kernel fusion, for instance, means if I have a couple of for loops over the same vector, then you want to fuse the operations within the for loops if the dependency graph works out. The scales, and yeah, that's probably the more meaningful thing. So, and we have currently a rather perplexing thing, which is that our GPU code is slower than our CPU code. So if somebody is willing to help us with this, this is not a good situation to be in. Now you might wonder, are those guys just stupid, right? Because I mean, GPUs are faster than CPUs. Everybody knows that, right? Well, the thing is you have a graph. Graphs are sparse data structures. Sparse matrix linear algebra on graphs isn't that easy. We're working on some ways how to work around this, but this is non-trivial. And especially if you have very large graphs, that might, let's say you need for the embedding 1 terabyte or maybe 4 terabytes, or maybe you have a couple of machines, then you're starting to strain at the edges of network bandwidth, because you might only get 40 gigabit per second between machines, or maybe 100 gigabit on the latest P3DNs. But your main memory bandwidth is still significantly faster than that. So your main memory bandwidth is probably in the order of 100 gigabytes per second. And you're not going to get the 100 gigabit exactly. You might get maybe 80 or so in practice, depending on how you write your code. So that's where you can see that you already win an order of magnitude in terms of bandwidth. Now, for planar graphs, or graphs that are nicely partitionable otherwise, this should be a lot easier. Expect a lot of work and progress in this area. Just to show you, well, how bad things are. So this is a utilization diagram. And essentially, every solid line means the resource is being utilized. And when it's not solid, and there's something right in between, it means it's doing nothing. This is a bad picture, basically. You want to have really solid chunks. We need your help. We also probably need your help on this. So these are our Google Analytics data. And, well, you can see that the adoption in India is about as high as in Hong Kong. I think you guys can move this up here, maybe even there. Right. So I would like to see this light up. And with that, I think I've told you enough about graphs, and you probably deserve a break. So this is still very much work in progress. I think it's good enough by now to start using it for production workloads and large problems. If you care about the systems side, help us. If you want to build new models, try it out. Tell us what you don't like, and we'll make it better. And thanks for coming along today. Take it, or maybe I've scared people off, right?
I guess, so let's begin the second half of the talk.
Let me just see whether that works.
And are we expecting some nice demos this time?
I was hoping to give you some nice demos, and right now I have the usual thing that happens whenever there's a demo. So it happened very nicely.
Yeah, good demos often have problems.
Okay, yeah. Okay, so basically, it's not doing what it's doing. This is OpenCV not behaving in the way it's OpenCV is supposed to run. Okay. The demo will be a little bit less fancy, but it'll still work. Okay. Good. So let's start with computer vision. And so I'll talk a little bit about that. Computer vision with GluonCV. Okay, this is supposed to work. Apparently it works if I stand next to it. Okay, so I'll talk a little bit about, why we built GluonCV, some of the models that are in there, how to process data, and the larger ecosystem that goes with it. And so the first thing is, you might ask yourself, how do you beat the state of the art, right, in computer vision? And that sounds like a, super question, right? So, go and write a better paper, you come up with a better network, but quite often that doesn't take care of it, right? So there's this very nice graph, not for computer vision, but for the ACL conference. And somebody plotted a diagram of, oh, yay, that's awesome. Somebody plotted baseline versus paper for the same problem for the conference submissions, right? And of course, this is chance. And okay, so they got something like this, right? So this is good, right? So the performance of the paper is better than that of the baseline. Okay, but you see what's wrong, right? Because you can't have the situation where different people have different numbers for the purportedly same baseline of what the state of the art is, right? Right? Because if somebody is up there, then any paper that doesn't even get there should be rejected, right? So in other words, while everybody claimed to be comparing to the state of the art, very few of them actually were. And this is for a major academic conference. And so the first thing you need to do is, if you want to beat the state of the art, is you need to actually catch up with it. Okay. And that's what we are trying to do to help you with by, releasing GluonCV. Oh man, that was definitely too much. Okay, I give up. Okay, so the first thing you want to ask, what did we set out to accomplish? So we wanted to match or beat the published state of the art for all the models in GluonCV. So that sounds like, match, hey, you just read the paper and re-implement it. And well, if you do that, it usually doesn't work so well. But we made sure we did well and did even better. And on this graph, this is speed, this is accuracy, and you want to move in this direction. And so you have mission accomplished there. You can get all the models from the same model zoo. So if you want to switch a mobile net with a squeeze excite net, version 150 to, with 152 layers, you can compare, right? And that's, a simple one-line code change. Comes with tutorials. You can download the trained weights. You can train your own. Comes with Jupyter notebooks. Fairly clean API design. Of course, it's open source. And if you have questions, we'll probably try to help you. And yeah, so this is probably the most striking one. So these are the published results for YOLO. The ones on top are ours. Same network, same architecture, but yeah, a lot more accurate. What do we have in the network? So in GluonCV, we have pose estimation. So that's the pose estimator running on a video, and I think it works kind of okay. So re-identifications and GANs, there's some work in there. Expect a lot more in that. Key point detection and depth prediction, expect a lot more in there as well. So this is basically what you can find right now. Why did we build it? Well, on one end, we have a couple of teams in Amazon that need good computer vision, so we support them, both internally and also for our services. The other reason is simply we want to make sure that everybody can use computer vision efficiently, for instance, on AWS. So let me show you a simple problem, namely classification. So basically, if you show this picture, you want the network to say dog. Okay. Simplest case is, digit recognition, or what kind of car is it, or face recognition, right? And we have a fairly comprehensive model zoo. So we have AlexNet VGG, ResNet MobileNet. We've got some network architecture search networks, but that's still work in progress. We've got ShuffleNet, and pretty much anything major, we've probably got it. But you need a lot more for that. You need, data preprocessing. You need an optimizer. You need various loss functions, metrics, and you need good acceleration for multi-GPU training and serving. And yeah, I give up. So preprocessing sounds kind of obvious, but I'll tell you a fun story. Actually, it wasn't so much fun for us. So here's an adorable furball, and if you perform any of those transformations, you still want to have an adorable furball, right? So this is essentially what you get by cropping, by changing the hue and so on, and brightness. And if you combine both, you get something that by now you need a little bit of fantasy to recognize it as a cat, but yeah, okay. This is how you get robustness. You want to have a number of different optimizers, because not all of them are always good. We've got 12 or 13. If you want to add a new one, that's maybe about 10 lines of code. Okay. So then, by the way, just on that, a quick anecdote. So when we got started, we tried to, match the state of the art, and we built stuff, and it didn't work. I mean, the team went as far as this was still when Torch was a thing, to actually add the Torch library as a submodule into MXNet. And we tried everything. We tried to replicate the results, and we couldn't. And then, turns out, okay, does anybody have an idea what we did wrong? So the network, everything was fine. And I've already said, well, it has something to do with preprocessing. Where in the preprocessing pipeline do you think you could screw up? If you match all the croppings and everything, right? We compared that, it's all the same. Network's the same, the activations are the same. Where could we have screwed up? Normalization? No. So what happened is that the JPEG decompressor was different. Okay. That cost us like 1 or 2 percentage points. Okay. This is why I'm saying catching up with the state of the art is less easy than you think. Okay. And so then you also want to have different learning rate schedulers, and I would argue that by now we understand less about deep learning optimization than we did a couple of years ago. It's supremely frustrating, but as of right now, that's the thing to use, the cosine schedule. Why? Well, for this one, at least I had some theoretical explanation. For this one, I'm totally lost. So you ramp up slowly for a burn-in, and then you decrease the learning rate. And that works really well. So forget about differentiable learning rates or other things. People like to write papers about cool features, but that's the thing that actually works. And then you do a couple of other things. Mixup helps. So this is another effect, if you will, data preprocessing, where you essentially alpha blend between 2 images. Let's say I have the image of a cat and of a dog, and I alpha blend between them, 0.9 cat, 0.1 dog. You basically want the labels, the conditional probabilities to match this. And then the other thing is, it turns out that you may want to be even more robust than what your logistic offers by smoothing out the labels a little bit from 0 and 1 to 1 minus epsilon and epsilon over n minus 1. So the next thing is, and of course this, because it's neural network, so it has a different name. Rather than function approximation, it's called knowledge distillation. Right? Because if it's knowledge distillation, I'm cool, right? I'm extracting knowledge from that poor network. So what is it really? You train a network that's maybe really expensive to evaluate, but fairly accurate. And then I take a smaller network and I basically try to perform function approximation using labeled and some unlabeled data to match the function values from one class with the other. And that's a well-known thing, but if you call it a different name, you can become cool again. And then transfer learning, that's actually a really useful thing. You could think of basically everything up to here, right, as your kernel, and then you basically have a Gaussian process or support vector machine by just saying, well, I just want to learn the last layer. Effectively, transfer learning or fine-tuning does nothing else than, just, fixing this and just training the last layer. Or maybe you only slightly tweak this and you mostly learn the ladder. That works quite nicely. This works a lot better than a lot of neural architecture search, just because pre-training on a large data set gives you an amazing amount of prior knowledge and good feature embeddings, much more than what you could do on a smaller data set with architecture search. Now, if you do both combined, well, yeah, okay, you're going to burn a lot of compute. So the world probably only needs 1 or 2 of those experiments a year, namely whenever there's a much larger data set available. There's a good summary of all this bag of tricks, and if you look at it, then you'll see that in a lot more detail. I gave you maybe a slightly glib summary of some of those ideas, but yeah, Tonghae and co-authors, on my team, they did a pretty good job. So then, well, you sometimes might want to do better than that, right? And I'll actually, let me just show you what happens if you don't. Let me quickly run that demo. Okay, so this eventually should just... Okay. So this is image classification applied to this room. Okay. And yeah, okay, it's Mr. Blurry Cam. And this is the best that you can currently do using ImageNet data. So it's pretty awful, right? We're in a library and some people in the room look like a grand piano. Okay, so yeah, it's terrible. Okay, but that's state of the art. This isn't me pretending to be stupid. This is actually the best you can currently do. So that's clearly not what you want. Okay, let me show you what you do want. But for that, I first need to kill that thread. Okay, capture device, run. Takes a few seconds. Sorry. I'll show you the Jupyter notebooks in a moment, but yeah. Okay, now we're actually looking at something a little bit more interesting. Please. Okay, the frame rate's all full. Okay. Yeah, sorry. This is okay. It's the point of a live demo. Let's see. Yeah, now we have it, right? So this looks a lot more like what you would expect. And yeah, it detects some chairs, and it would detect some other things too. Okay, so I guess you get the point that this is what you want, right? Why? Because okay, it's detect. Okay, thank God I'm a person. Let me stop this. Tear down. And yet, I suppose estimator and other stuff as well. So, because if you have multiple objects in an image, then classifying this as, I don't know what exactly, doesn't really do the picture justice. You want to know there's a couple of people, somehow chasing after a ball, right? So you want bounding boxes, right? There's a dog, there's a cat, and you want to measure things, for instance, based on, the Jacquard measure, basic intersection over union. By the way, until when do I have time? Till
Up to you. Usually the plan was till 5:15.
okay.
Go ahead.
I'll hurry up a bit. So there's a couple of popular models. And by the way, how you decode this is fairly straightforward. You basically pick the best candidate. You then knock out all the ones that overlap significantly with your proposal and are worse. And that's called, because you need a new name because it's deep learning, non-maximum suppression. And then, okay, you basically repeat this, and that works quite nicely. And yeah, it's all in Gluon. So let me show you a little bit how you would accomplish this. Simplest case, there's this thing called single shot multi-box detector, and you basically propose something, and so you propose an anchor box. So there's like the approximate region where an object might be, and then within that you fine-tune exactly where it is. And you do that at multiple scales, such that if there's a person in front and a tiny elephant in the back, because he's far, far back, you get both right. And this is fast and easy to implement, and it doesn't work very well. But yeah, it's kind of the obvious thing to do. And here's the network diagram for that. So why is it not so good? Well, because you basically don't really have a lot of intelligence at those first few levels, and only up here would you be able to detect really well. Right. So what's to be done about this? You use YOLO. That's much more accurate. So what they do is they basically say, well, let's actually predict at all the scales at the same time. So you do something that looks like in a fully convolutional network, you get to some final resolution, let's say 7 by 7, and now within those cells, you predict all the objects where they could be. And there you go. So this takes an image, divides it into 7 by 7, right? For every one of those cells, it tries to estimate what might be there, like a bike or a dog or something. It predicts, bounding boxes at various scale. And then you decode as mentioned before. Now, of course, there's always the brute force alternative. Brute force alternative is you take an image net, you just scan over the entire image, right? For various frames, and you check where an object might be. And since we have all those objects, well, that's great. Trouble is, this is ridiculously expensive because it takes forever, right? That's why it's called region CNN. And then in the end, well, they used an SVM for classification. I'm not quite sure why they did this, but yeah, I guess they had maybe an SVM solver sitting around. But it's very expensive. It's a better idea, and that's why it's called fast RCNN, because it's faster than the regular one, is you actually pool over regions of interest, over the cattishness or whatever, and then by doing so, you get some computational savings, and you still need to guide your search algorithm. But anyway, so this is better. And then, because fast RCNN is still very slow, people made it faster still, which is still a very slow algorithm, but it's faster. And we basically replaced that selective search by a deep learning strategy. Anyway, now, how do you actually make this thing accurate? Well, what you can do is you can use Mixup, so the thing that I mentioned before, the alpha blending also for detection. If you look at the picture on the right, yeah, there's a stop sign and 2 sheep. That's what you want to get. So this is where we are now. So this is the lift over regular YOLO. And actually, let me add this nice animation where there's actually an elephant in the room. And okay, so why is there an elephant in the room? What are we seeing here? That's speed versus accuracy. That's log scale. So faster RCNN is really, really awful, right? And until our paper, it was just so much more accurate than YOLO. Now it's still more accurate, but not quite that much more. Now, why does Mixup help? So if you, for instance, look at those labels here, this is trained with Mixup, this is without Mixup, and you can see that the labels flicker around a lot. Here they are much more stable. And yeah, okay, it pretty much keeps the dining table the same. It just moves it a little bit around where it is, but overall, that's much more accurate, and that's mostly due to Mixup. So then, a couple of other things you can do. You can do segmentation. So this is our beautiful new office in Palo Alto. Well, actually East Palo Alto, which is the not so fancy part of town, but the building's very nice. And this is using our segmenter applied to this picture. And yeah, okay, there are cars and trees and buildings and street signs and whatever. So how would you build one? So you basically take an object, you want, or multiple objects, and you want to segment them apart. And well, with segmentation, you get the stuff on the right, but without, you get this on the left. But that's still not good enough. So for instance, if I look at the room in the back, I can see people sitting close together. And so if I use computer vision, then I will infer that there are lots of Siamese twins in the room. Okay, it's not good. So you want to have instance segmentation rather than semantic segmentation. That separates this. Anyway, so this is what you get with semantic segmentation. And again, you use the IOU, so intersection over union measure, to find out how well you're doing. And so now, how do we actually design this? The simplest case, you use what's called a fully convolutional network. This does pretty much exactly what I mentioned before as well. So you train maybe your ResNet with a tabbycat, and in the end, you get those 1,000 dimensions, 1,000 channels, and just one dimension, and you just scan over the entire image. This is called to convolutionalize an image because, well, we needed a new name, right? This is what happens. This gives you this heat map. For instance, for the top 5 predictions, or for barbells, if we want to detect barbells. So now, what does this have to do with segmentation? Well, you use this in combination with a segmenter to inpaint what the object is. And so this works quite well. Or sort of, kind of. And the thread is actually similar to before, because it's easy to implement. You could do better. Now, what's really happening? Well, what's happening is that basically as you go and go through your convolutional neural network, you're losing resolution as you progress, right? As you pull, in the end, well, you're done. So that's not so good, because that means that the position accuracy of your that afterwards what goes into your segmenter is very bad. So you need to keep the resolution high, and you can do that by either upsampling between layers, or by simply using what people called, in a very atrocious way, atrous convolution. So basically you have skips in between. It actually comes from the French word atrou, with holes, but yeah. You do that, and if you use those dilated convolutions, you get the higher accuracy just because you can retain the pixel level accuracy up until the end. And of course, this is slower. So this is what you get here, dilated ResNet, and yeah, that works quite well. So then, well, you use that with a segmenter and you get a nice segmented image. So the problem is, if you do this, you're not very good at multi-scale image analysis. Because, well, we are just scanning our image at the same resolution. And if I have, a small elephant and a large human, the large human will do fairly well, and the small elephant, well, poor elephant. So instead, what you can do is you can have multiple resolutions at the same time. And you do this basically 4 different ways. That's called the pyramid scene parsing network. And if you, slow and accurate, but if you really do this properly with address convolutions, then you get something that's very slow and very accurate. And if you use our friend, the faster RCNN, as the detector, you get something that's extremely slow and a bit more accurate. Okay. By the way, yeah, we're still slow. We're slightly more accurate than published papers by essentially using a couple of tricks. Now, data processing, yeah, you need to worry about this. I already mentioned a bit about that before. So, yeah, basically, you have a nice processing pipeline. You want to make sure that your deep learning framework takes care of that through iterators fairly nicely automatically. You just define the processing steps, and you then just incorporate that into your data iterator. And it takes care of multi-threading everything, because Python, of course, is awful. So if you don't multi-thread, it doesn't work very nicely. Or you just push everything onto the GPU, which is using NVIDIA DALI, basically using NVJPEG. That's currently work in progress. That'll be quite a bit faster still. So in summary, how do you beat the state of the art? Well, we can help you. So let me just spend 2 more minutes on a bit more of this ecosystem around it. So we already talked about deep learning on graphs. Then, because there's GluonCV, there also has to be Gluon NLP. And so if you want to do NLP, again, same deal as before. We help you beat the state of the art. And, maybe you contribute back an extension. This all sits on top of Apache MXNet. Go to the beta site, that's better engineered. It'll soon become the regular one, but that way you can find stuff better. And then, so yesterday, the Chinese translation of our book went into print in China. The English version will take a little bit more time because we are still adding more content. It's about 150 notebooks. If you want to teach from it, so for all the lecturers in the room, we have slide decks, about 20 of them with 50 slides each. You have Jupyter notebooks, 120 videos. There are a lot of homework assignment sheets there, so you can probably reuse some of those. So the difference to your regular textbook is that it's all written in Jupyter. So we didn't write it in LaTeX, but in Jupyter. That causes a little bit of issues at the way how you write. But then at the same time, it means if you want to actually understand how some of the code works, you just execute that chapter. Right? So if you want to have a ResNet, you execute the ResNet chapter. You can directly muck around with it. We did this because we wanted to make sure that it's very easy for people to learn from that. We just finished the undergrad class in Berkeley last week. That's why I could only travel this week, because there was still teaching on last week. And yeah, it's open source. By now it's over 600 pages. Apologies for the references being a total mess right now, because we only got a working reference citation system that works for multiple Jupyter notebooks maybe about 3 weeks ago, because Jupyter was never meant to be used for writing books. But now you can write books. There's a website that has all of this stuff. So if you go to d2l.ai, I would say it's probably a lot more fun to read it online rather than as a PDF. But you can kill trees if you want to. And more importantly, If you don't like something, send us a pull request. So this way, the erratum gets incorporated within hours, whereas if you have a dead trees version, it takes years. Right? And here's the deal. If you send us a pull request with a meaningful update, rather than just, hey, you missed a comma, right? But, maybe a couple of words or whatever, so that's what I mean with a meaningful update. We will send you a copy of the book, of the English version. I don't think the Chinese version is going to do you much good once it goes into print, which will be with Cambridge University Press. And we'll acknowledge you. Probably by your GitHub handle, so pick a nice one. And yeah, if you want to teach from it, let me know. Okay, with that, I think I've taken more of your time than I probably should have. So thanks for staying on until now.